Hello and welcome. In this video series, we're going to get into the ideas behind logic, propositions, and being able to really analyze arguments or analyze statements and describe whether those are logically valid or not. So this deals with things like Boolean algebra. We'll get into the notion of truth tables and working with Boolean logic. For the most part, our approach to logic in this class will be geared around Boolean logic. And the reason for that is because oftentimes we want to make justification or prove some sort of theorem. And in order to do so, we have to have enough logical constructs in place to do that. So here we'll just introduce some of the key features of logic and propositions and learning how to analyze statements. So first of all, a proposition is a declarative statement that is either true or false. Whether it's true or false, though, it is not important in terms of telling whether it's a proposition. If you can either say that the statement is true or false, it is in its own right a proposition. So which of the following are propositions? True or false? I am a human being. Well, that's either true or false, and for each creature that might vary, but in general that can either be a true or false statement, therefore it is a proposition. Am I a human being? Well, I don't know. That's not a declarative statement. That therefore a question can either be true or false. The answer to a question can either be true or false, but not the question itself. X plus 1 equals 2. Sure, well, depending on what X is, this is either a true or false statement, therefore yes, it is a proposition. Read this carefully. Oh, wait a minute, that cannot be a true or false statement. I read this carefully could be a true or false statement, but read this carefully is really just a command. So that is neither true nor is it false. So in order to wrap structure around logic, we typically use variables to encapsulate a proposition. For example, in the statement, I am a human being, we're just going to replace that entire sentence with the letter H. Therefore, when you see the letter H, that stands for I am a human being. The reason we want this is we often want to take a more complex statement and turn it into symbolic logic. It's much easier to analyze a sentence or a paragraph that has a lot of logic loaded into it by using logical symbols and to analyze it with such things as truth tables. So look at this statement. If the return value of the function is true, or there is an exception thrown and no traceback, then either the main loop will preemptively terminate or a conditional statement will execute the alternative subloop. Well, on first look, you may be a little bit confused by what that statement is really saying, but if we were to impose some symbolic logic, it might make a whole lot more sense, and we could analyze it in a very mathematical way. So this is not unlike something you might encounter in coding logic where you need to take something like this and build it into code. However, it may be a bit tricky to understand what this is really saying and what actions may or may not happen. We would prefer to write this statement as something like this. So I won't go through the details of what these symbols are right now, but this breaks up this complex or compound statement into a series of simple statements. So actually the letter A stands for the return value of the function is true. B is there is an exception thrown. C is no traceback. This little V operator, that's actually the word or. So when you connect two simple statements with a disjunction, we'll talk more about this soon, then you can actually take a series of simple statements and combine them to form that compound statement that you're interested in. At first sight, this may not be something that looks fun to analyze, but it allows for the construction of a truth table, which we will soon introduce. So as there are statements, it's important to be able to talk about the negation of a statement. So the negation of a proposition, we'll call that proposition P, is denoted with this little like sideways backwards L, and that is read as it is not the case that P, or you could say not P. Now I'm okay with you using a similar statement. I know some people have seen this before for P naught, a P with a little prime above it. Some people maybe have even seen a P with a bar over it to say P not. These are all okay, but logic often uses this L symbol to denote not. But you can use whichever one you want, just be clear about it. So for each of these, write the statement that represents the negation for each of the following. I am a human being. Well, what is the negation to say it is not the case that I am a human being? Well, to say that it is not the case, we don't want to just say it like that because it is not the case that I am a human being just sounds funny. It makes more intuitive sense to say I am not a human being. Okay, what is the negation of I will not go to class tomorrow? Well, we could again say it is not the case that I will not go to class tomorrow. But what does that really mean? So this in itself is kind of already the negation of the statement I will go to class tomorrow. So we could say I will not go to class tomorrow. But that really means that if I won't not go to class, then that means I will go to class. I know that sounds kind of funny, but it makes more intuitive sense to just say the kind of the opposite of this, if you will. I will go to class tomorrow. And what about the statement x squared minus 3 equals 13? Well, if we first of all start off by writing it is not the case that x squared minus 3 equals 13, then what does that mean, that x squared minus 3 does not equal 13? Oh, wait a minute. That means precisely x squared minus 3 does not equal 13. So if it's not equal to 13, if the square of x minus 3 is not equal to 13, then this can imply one of two things. It could be that x squared minus 3 is less than 13, x squared minus 3 is less than 13, or x squared minus 3 is bigger than 13. So that's the only way for something to not be equal to something, is it has to be either smaller than or greater than it. Okay, y is greater than or equal to x. Well, let's think about this on a number line. If y is greater than or equal to x, and this is x right here, and x, currently the statement says y is greater than or equal to that, well, the negation of that would say y is, it is not the case. It is not the case that x, or that y is greater than or equal to x. So what would be the negation of that? Well, if it's not greater than or equal to x, that means the only other possibility is that that y is less than x. And this is just a parenthesis to indicate that it cannot be equal to x, but it can be less than x. So if y is not bigger than or equal to x, that means y is less than x. That's the only other possibility. Okay, y is not equal to x. Okay, so it is not the case that y is not equal to x. Well, okay, so if it is not the case that y is not equal to x, y is not equal to x, and so that really means that y is equal to x, would be our final statement there. Final statement here was this guy, and our final statement here was this guy. Or you could, in this second bullet point, you could have said this in lieu of x squared minus 3 is not equal to 13, but this was just a little bit more compact. So that's dealing with negations, and negations are going to become incredibly important because sometimes when we justify a statement or we want to prove something, talking about negations in something called contrapositive will be much more helpful. So given two statements, P and Q, let's define something on those statements. So P and Q are actually simple statements. And all we mean by simple statements is that there's no and, there's no or, it's just a basic sentence. Like, I am a human being is a simple statement. I will not go to class tomorrow is a simple statement. But if I said, I am a human being and I will not go to class tomorrow, that is not a simple statement because the and is a conjunction. It conjoins those two statements together. So we want things to be simple statements because they're far easier to analyze. So if we have two simple statements, P and Q, the conjunction, so think conjoined twins that are joined together, the conjunction of these statements denoted P with an upside down VQ. That's read as P and Q. The conjunction of these statements is P and Q, is the proposition P and Q, and is only true whenever both propositions are true. We can represent such statements using a truth table to see when the conjunction is true. Okay, so let's first of all start off with looking at P and Q and figuring out what the possibilities are for P and Q. So this is often one of those things that when we look at the truth values of P and Q, now P and Q we've defined as propositions, and propositions are either true or false. So if I first start off building just a little tree diagram to see this for P and Q, so we can say that P could either be true or false. And actually, instead of doing true or false, I'm going to do false and true. That's the same thing, but P could either be true or false. So this is statement P. And then if P is false, then Q could still either be false or true. If P is true, Q could still be false or true. These are independent statements. And so we can see in our truth table that P and Q could be false, 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 true, true, false, or true, true. So those are the different values that we're going to list in our table. And if you notice that the innermost statement, if you alternate false, true, and then you double the number of falses, false, false, true, true, and then if you had another column, another statement, you'd have 4 falses and then 4 trues. So the statement P and Q will only be true if both of your input statements are true. So in other words, if P and Q are both false, then the statement P and Q will be false. If any one of these is false, P and Q will be false. An and is only true when both of the simple statements are true surrounding it. So that is the key situation here, that an and statement is only true when both of the propositions are true as well. So with that said, let's look at an example. Find the conjunction of the proposition P and Q, where P is the proposition Rebecca's PC has more than 16 gigabytes free hard disk space, and Q is the proposition the processor in Rebecca's PC runs faster than 1 gigahertz. So the conjunction of these is just going to be that Rebecca's PC has more than 16 gigabytes free hard disk space, and the processor in Rebecca's PC runs faster than 1 gigahertz. Okay, so this would only be a true statement. In other words, you would not call me a liar if I told you Rebecca's PC has more than 16 gigabytes of free hard disk space and the processor runs faster than 1 gigahertz. The only way in which you would call me a liar is if both of those things weren't true. So if you think about our truth table back up here, you can think about the situations that result in a false as being lies. So if I had an and statement and either of the two simple propositions were false, then you could call me a liar. Like if I said, I will post these notes and I will post the video, but I don't post the notes, but I do post the video, then you can call me out as saying, hey, you said you would do both of these things, but you didn't. So the only situation in which an and statement is true is if both of the propositions in the conjunction are true as well.